Students, welcome to lecture number 40, and this is the last lecture on this course. So, what we are going to do in this class is, first we will discuss whatever pending I have talked about it in the last lecture, and we will spend quite a bit of time on summing it up. Why? Because we have learned different kinds of topics, and I would like to tell you in a brief what you have learned and what are the things we have could not learn much, where you have to go much deeper, and how we can actually structure that. But this is something which is a very interesting thing, that when you always end a course with the last lecture, we always feel little bit nostalgic. And during the whole semester where the course was run, we tried our best to make you aware of different aspects of these advanced topics, both machine learning and deep learning. And at the end, I talked about a new topic called material informatics. And I have been thinking about this material informatics topic quite a lot. So, now we are planning to develop a new course on this subject, because this is something new and it might be a very important topics of understanding in the near future. So, this is the part 4 of material informatics, or what is known as the materials knowledge and materials data science. And as you understand, data science has become an integral part of our life, and it has been taught in various subjects, whether you talk about economics, mathematics, statistics, or management sciences, as well as different branches of engineering sciences. And this materials knowledge and especially data science have become an important field of research. Why? Because you have a lot of data available, that is the first thing. Once you have plenty of data, how we can play with the data, that is something that always comes to our mind. And in the sense, we have to play in a way that we can generate knowledge. And by generation knowledge, I mean understanding the data in a way, subtle way, so that we can understand how we can develop the knowledge. And from knowledge, we can actually discover. That is the idea. So, what I am trying to say is that data which is available to you can be processed to find out patterns that can provide us knowledge, and knowledge can provide us discovery. So, final goal of any such course or any such aspects, whether it is a machine learning, deep learning, or material informatics, is to discover or design and discover new materials with target set of properties. That is the idea. And so, therefore, in that purpose, in that thought, or in that aspects rather, knowledge is the key aspects, key thing. Can we garner a lot of knowledge or more knowledge from data? That is the material informatics or material data science talks about it. So, as I told you, material informatics is a very new subject, and you will not find much literature. There is no specific book available in the market, and only there are edited books or edited papers or some fundamental review papers are available, on which you can actually rely on your knowledge. So, as you can see, papers by Professor Krishnarajan and Professor Hassan Mubarak are very interesting and important. Other than that, I have listed 2 books. One is by Michael S.P., other one is by Jiawei Han et al. And these books are also going to provide you a lot of topics. We are going to cover a lot of topics on this subject. So, as I already told you, material informatics is something to do with data science, and data in the sense can come from simulations, it can come from digital libraries, it can also be obtained from combinatorially derived data sets. Once you have different data sets, you can combinatorially connect them and make new data sets. Well, these are all can be easily done, but data can come from mostly from experiments, and these data are stored in the digital libraries. We can also get data from data warehouses, and these data warehouses are available in various parts of the world, where you can actually take data from them and do analysis. So, once you get the data, what all you can do? We will do a lot of analytics with the data, right? And these analytics are what the machine learning and deep learning actually are related to. So, we can do simply we can do separate vector machine based analysis, which is nothing but a classification problem, which it can easily separate data which are important to us, which are not important to us. Also, it can do a lot of other things also. And second thing you can do is data mining, right, which we have spent a lot of time in the last lecture. Data mining is a big subject, and we have spent quite a bit of time on discussing about that. And other than that, we can do some amount of analysis like principal component analysis, which we are going to talk about today, as well as partial least square analysis. These are nothing but a least square analysis, which I have already discussed. SBM is also I have discussed about it. So, SBM and partial least square analysis I have discussed, and some part of mining, data mining I have discussed. Today we are going to talk about a little bit about PRINCE or principal component analysis. Now, we also can develop theoretical understanding that can provide us knowledge, right. So, what are the theoretical models you can use? You can use atomistic based models, right. That is one of the things which we all do simulations using atomistic models like DFT or MD simulations, where you can consider atoms and subatomic particles and do a lot of modeling. So, once you put this thing together, data analyze using this kind of approaches as well as theoretical understanding of the subject, this can provide us knowledge, and the knowledge base is what is important. That can provide us insight to design the materials. So, key aspect is your information or knowledge, right, or information or the data rather, right? Correct, that is the key aspects. So, information or data must be stored, and that is why we need huge space to store the data, and this can be done in digital libraries or data warehouses. So, as I told you, from bytes to kilobytes to megabytes to gigabytes to terabytes to we can go down up to exabytes, right, YOTTA, right, this one YOTTA byte, that is about 2 to the power 10 exabyte, and that is about 2 to the power 10 zettabytes, that is about 2 to the power 10 petabytes. So, 2 to the power 10 to 2 to the power 10, and that has become 2 to the power 20, 2 to the power 100, right, to the power, no, 2 to the power 20, 2 to the power 30, 2 to the power 40. So, 1 terabyte is 2 to the power, 1 exabyte is 2 to the power 40 terabytes. That is massive, right. That is a massive amount of data we can get and store, and that is what is going to happen in the next 10 to 20 years. You are going to see huge digital libraries where data will be stored. By the way, many of these facilities which are available across the globe, like synchrotron radiation facilities or facilities with electron microscope centers, they actually generate a lot of data that can be of the scale of if not exabytes, it can be the scale of exabytes, and that is massive scale of data are also part of digital library, and that can be put in as a digital warehouse. Now, we talked about data mining. Let us spend a couple of minutes on that. It is nothing but extraction of the interesting patterns of the knowledge from the huge amount of data. Remember that data mining does not mean just like what you think about mine. In mining, what do you do? We can dig deep and find out whether there is a coal or there is a diamond or there is something else, iron ores or the present of there, right. That is why there is a traditional way of thinking mining, but here that is not the meaning of data mining. We are not going to go somewhere and try to find out data, that is what we are not doing. What we are trying to do is we are trying to extract interesting patterns of knowledge from the huge data. Remember, after a few years data will be available to everybody, because we have a lot of discussions about the open data science, where everything will be kept open. Anybody can take the data and analyze it and find out patterns. That is what is called data mining. So, data mining is extraction of these interesting patterns. It can be implicit, it can be previously known, or it can be new, it can, in most cases is potentially useful, that is what it is. So, explosion of data growth from terabytes to petabytes to exabytes to terabytes, whatever, data collection and data availability is an issue right now, because most of the cases they are not easily available, but I understand or I believe after a few years data will be available to everybody, and then once you do that, then you can actually do this analysis. Now, can you do automated data collection? Can you do also automated analysis of massive data sets? What I am trying to say, can data mining to be done automatically or not? Well, yes, it can be done. Thanks to ML and DL, we can actually do that. So, the two primary functions of any data mining is, first is data recognitions. This approach serves the basis for deriving correlations, trends, clusters, trajectories, anomalies. That is the idea. So, we want to find out how data are correlated, what trends they are going to provide, whether you can cluster data in different ways, or we can actually find out trajectories, or we can find out some outliers. That is what is called data recognitions. That is the first step or first function of any data mining approach. Second important function what is it is predictive modeling. Can I do predictive modeling of that? And that is why I gave the example of atmospheric modeling or weather prediction, right. If you probably know that weather prediction is very difficult, because weather is a global phenomenon. Something happening in Bay of Bengal can affect weather in New Delhi. So, how you to model it? So, modeling of that requires extensive uses of data science. We have to collect information about the weather parameters, temperature, pressure, moisture, many other parameters, I guess. First collect the information for across the whole region and then put it in a model, analyze it, then only you can predict. So, therefore, this predictive modeling is outcome of the data analysis, and that is what final goal of any data scientist. Any data scientist, whether they are working with atmospheric modeling group, or they are working with some food giants, or they are working with some business giants, their job is to analyze the data and make a predictive modeling. And this is what is normally is a part of whole exercise. First, you have to find out all the data sources. We talked about it, different kind of databases. We can actually create databases using NLP, natural language processing, and like using web of information, scientific experiments, or whatever available with us. We can create databases using NLP. Once you have databases, then we have to do little bit data preprocessing. That also I taught you, right? Different kinds of data preprocessing needs to be done, and integration of databases also. Then we can keep the database in either digital libraries or in the data warehouses. This term will keep on to you, data warehouses, because this what is a business model, right? We can keep data in a warehouse and sell it. So, after that we can actually do data exploration, data mining, and finally we can visualize the data and make decisions on that. So, data exploration means using all kind of statistical tools, sequential query language, what is called SQL, or you can actually do other kinds of approaches like whatever machine learning models you have learned. Data mining is very important. You see, information discovery, we have to find out the inherent patterns in the data, and most of the cases these inherent patterns can be obtained even by plotting or visualization of the data, and finally decision is made by the end user. So, this is the tree or pyramid which you are going to follow when you talk about data mining. So, data mining is a part of the whole analysis, it is not a subject alone, it is a part of the whole analysis, and it can be used for various kinds of purposes like machine learning, pattern recognition, statistics, applications, visualization, algorithms, database technology, high performance computing, everything can be done. So, as you talked about, main idea is the knowledge, and how do you get it? Well, as you know, this is what is called knowledge discovery process, or what we call KDD, and here you have databases available. You can do data cleaning or data integrations, they are part of data preprocessing, keep the data in the warehouses, and then you can take the task relevant data from the warehouses, do a lot of data mining analysis, and find out the pattern evolution that will provide us the knowledge. So, basically we are trying to say the same thing in different kinds of ways. And data preprocessing means data normalizations, data dimension reductions, data cleaning, feature selections and data integrations. Data mining means pattern discovery, classification and clustering, outlier analysis, association and correlation. All of these you have taught as a part of machine and deep learning. And after that we can do post analysis also, like you can find out pattern, what kind of pattern have formed in case of data mining, how good these patterns are, that is called pattern evaluation. And we can also do pattern selections, which of the patterns are actually good for predictive modeling. And there will be data scientists which will interpret the patterns and then we will do kind of decisions made. So, first of all, this is a multidimensional view and we have to understand why we want to do data mining. This is an extended relational object oriented heterogeneous legacy, and we have to mine the knowledge. So, we need to do characterization, discrimination, association, classification, clustering, trend or deviation, outlier analysis, all these things you can see that. Characterization means preprocessing, discrimination, association, classification, clustering, trend and deviation, outlier, etc. Idea is to do predictive data mining or predictive modeling, and many cases you can also do multiple or integrated functions also at the time. And we use all kinds of techniques like data intensive data warehouses, machine learning, statistics, pattern recognitions, visualization, high performance computing, everything we can do. I do not want to get into details of the warehouse which we have discussed, and data warehouse is subject oriented, integrated, time variant, non volatile collection of data. Remember these words: subject specific, integrated, all the data of the subjects is integrated, time variant, it has to be updated with respect to time, and non volatile, it should not evaporate, right. Data must be present in proper form, collection of data. So, it is always subject specific, whether you are talking about material science, you are talking about physics or chemistry, subject specific. And integrated means all the data together. Time variance means depending on, as data has to be corrected as a function of time. As you do an experiments, more and more experiments, you are collecting more data, how good these are. And this is something which is very important in making management decisions. That is what data warehouses do. They not only collect data, but do all kinds of things. They do time updation of data, they segment data. So, that is what is shown in this picture. It is a multi-tiered architecture. So, you can have data sources coming from different databases, either operational databases which are existing already, like we have operational databases like Pearson's crystallographic databases or thermochemistry databases or material property databases. These are all operational, these are all available to you. You can also have other sources data which you can create by using NLP. And then once you do that, then you create something known as a metadata, and which can be monitored and also integrated, and that is how they are actually kept in a data warehouse. Then you can have OLAP softwares or servers which can actually analyze the data, make data query language system and report. So, that is the front end tool. So, back end tool have data sources. So, this is in a nutshell is a multi-tier architecture of any data warehouse. God knows you may be one of those data warehouse managers in future. So, there you need to take care of these aspects. Now, not only that, once you have data, you also have attributes and objects, right. Like data objects may be customer, store item, sales, medical databases will have patients and treatments. Always you go to a hospital, they will first take your name, they will first look at whatever happened, then they prescribe treatments, everything is actually part of data, right. And university databases will have students, the professors, courses, like I am teaching this course will be listed somewhere, that is a database. Then you can also have attributes or feature, and normally databases rows and columns. Rows are actually data objects and columns provides you attributes, right. And attributes are nothing but your characteristics of a or features of a data, right, that we have talked about it. And then how do you first you have data, right, how do you find out what informatics of that. First thing is to do is basically central tendency. That is nothing but a statistical tool you always use, which is taught in the class room in class 10, 12 or maybe in first year of bachelor's. So, you find out mean, you can find out weighted mean, that is what is shown here. This is a weighted mean, this is also definition of mean. You can also find out median. Mean is nothing but a arithmetic mean, I am talking about it. One can also find out trim means, like chopping the extreme values, and median value is basically what? If it is a number of data is even, then median is n by 2 observation plus n by 2 plus 1 observation divided by 2. Basically it tells you if odd number of values are present, average of the middle two values. Otherwise it is, if n is odd, that is n is odd, then n is even, then it is not only the middle values, but n by 2 plus n by 2 plus 1 observations. Okay, that is what. Mode is what is the value which frequently occurring in the data. So, therefore, we know also that in statistics this equation is valid. You have mean and mode, you can calculate median. That is something which is always considered very important. Mean and median can also be used to create find out the mode, and we can also plot the data and find out what kind of trends are there, whether symmetric or skewed. Symmetric means you see there here the mean is at the middle of this, that is nothing but a Gaussian. You can also have positively skewed data and negatively skewed data, that is what is shown. Mean is on the left side for positively skewed data, mean on the right side for the negatively skewed data. This is something always find out. Another important aspect you can do is a box plot, right, which is nothing but 5 parameters: minimum, maximum, first quartile. So, minimum is the lowest value, maximum is the highest value. Then you can also add 3 important things, what is called a median, first quartile and third quartile. What is first quartile? We always divide the data into quartile, 25%, 25%, second quartile is 25 to 50%, third quartile is 25, 50 to 75%, the last quartile, right. So, Q1 is the middle value of the lower half of the data, and Q3 is basically middle value of the upper half of the data. So, all these 5 data are placed in a box, that is what is called a box plot. You can see lower extrema, upper extrema and your median, all these things are actually kept in one go. That provides you details of the data very easily. Now, one can actually do visualization of that. You can put 3D plots, you can see how it is, minima, maximum, median and the first and the third quartile data. You know that we can also do distribution, normal distribution, and normal distribution important aspect is mean and the standard deviation. So, mean is actually shown here at the center, and standard deviation is always sigma, and we can always make mean plus 2 standard deviation or mean plus 3 standard deviation. Mean plus 2 standard deviation and mean minus 2 standard deviation contains about 95% of the data, and mean minus 3 standard deviation and mean plus 3 of standard deviation contains almost 99.7% data. So, by that we can integrate the data and do that. One can actually do histogram analysis also. This is our visualization, right. That provides you graph display of the tabulated frequency, and it even shows the proportion of the cases fall in each of the subcategories, like here subcategory is blue, green, yellow, right, and it differs from the bar chart in the sense that the area of the bar that denotes the value is not the height as in the bar charts, and this is the crucial distinction when the categories are not uniform width. Categories are usually specified at non overlapping intervals with some variables, and lastly we can also do scatter plots. I am talking about scatter plot from real machine learning models which we performed. You can see here delta H mix and the Pauling radius, and this is the difference of electronegativity with Pauling radius. So, you can see the class scatter plots, right, easily. They provide the first look of the bivariate data to see the cluster of points, outliers. So, you can clearly see there is outlier right here. So, each pair of values treated as a potential pair of coordinates, that is what is shown here, pair of coordinates, and plotted as points in the plane, right. You can see the pair of coordinates like delta H mix versus Pauling radius, delta H mix versus change in difference in electronegativity, or delta electronegativity difference versus Pauling radius. This all provide you scatter plots. Most scatter plots, this is again for modeling, you can actually see how the scatter plots look like. They are very vital for machine learning modeling, and they actually provide you trends of the data. This you can see there is a trend here, can you see that there is a trend there, okay, there is a trend there, it provides you trend. So, you always make scatter plots whenever you want to do analysis of your data in machine learning and deep learning for any kind of material science problem. Scatter plots is the first thing we always try to do, other than the statistical analysis, right. And you can always see, you can also get positive or negatively correlation of the data. Left half of the fragment is positively correlated, this one, network, this one is negatively correlated. Okay. This is positive and this is a negative correlation. And here you see this is uniform data, more or less. There will be always some data which will be uncorrelated, which you cannot correlate with something. That can be always found out. That is good. Then you know that this axis, whatever you are plotting, they are uncorrelated, independent of each other. That also you can find out. Visualization is another important aspect of data mining. You can do geometric projection visualizations many ways, direct, scatter plots, I have talked about it. You can do box plots, you can do landscape, okay, persecution views, hyperslides, parallel coordinates. We do not have time to discuss each of these techniques, but these are all available with any software. Another interesting thing about material informatics is what is known as a dimensional stacking. You know, here you partition the n dimensional data or attribute space actually in 2D subspace. Like this is attribute 4 versus attribute 3 2D subspace of the n dimensional data. And this allows you to do a partitioning of the data in a very systematic manner. And you know, there actually we can find out which are the important attributes for which should be using in modeling. But it requires adequate amount of data. And we also require adequate amount of data with good reliability. But you know, it is sometimes difficult to present the data like something which is 5 dimension, 10 dimension or 9 dimension, then only we use this. And there we can actually take out 2 attributes plot in a that. So, dimensional stacking is that, it is basically we are taking n dimensional data and plotting in 2 dimensional space in such way that 2 attributes becomes very prominent one. Well, now let us talk about PCA or principal component analysis. It is a dimensional reduction technique, remember that, and it is used widely in machine learning, and it is used to simplify large data sets into smaller sets while maintaining the significant patterns and the trends. So, we do not want to disturb the trends and the patterns, but we want to basically generate data. PCA is kind of a machine learning technique that reduces the number of variables in a data sets while preserving the most important informations. It often used to analyze the large data sets, and it can help improve the performance of any machine learning algorithm. So, you have large data sets, you do not know how to reduce the dimensionality, this is what is required. What we do, we transform the large set of variables into smaller variables, that is what is the key thing. We transform large set of variables with a small number of set of variables, and in such a way that we do not lose any significant information about the patterns and the trends. PCAs are new variables, they are actually new variables that are constructed as a linear combination or mixture of the initial variables. These are the information we should always remember. These are linear combinations of mixture of the initial variables which we have started discussing about it. These combinations are done in such way that new variables, which are also known as the principal components, are uncorrelated, and most of the information within these initial variables is squeezed or compressed in the first components. So, let me explain it. See, this will be constructed in such way, these new variables or principal components are linear combinations of the initial variables or mixtures of the initial variables. They are not nonlinear combinations, they are linear combinations, and this combination must be done in such way the principal components must be uncorrelated. I talked about uncorrelated data, right? Correlated data, uncorrelated data, we have shown you scatter plots, all these steps. So, that such way these combinations must be done that they are uncorrelated. How do you do that? There is a mathematical way of doing that, we will discuss today. And principal component represent the directions of the data that explain the maximum amount of variance. This, remember these words, this is the maximum amount of variance, that is what is used in this case. The principal components are the new axis that provides the best angles to see the evaluated data, so difference between observations are visible. How do you do that? Okay. So, before we start, let us talk about what is variance and what is covariance. Variance actually talks about measure of the deviations from the mean point of the in one dimension. You already know mean, right, of any data sets. So, the variance talk about how much is the deviation of any data point from the mean, that is what is variance. Now, what is covariance? Variance is easy to understand. If I have a plot, let us say, and about two variables x, y and x, okay, and you know this data, this is the mean and this is my data point. So, we are talking about how far away this is, that is called as variance. Okay. And what is covariance? Co means two, right, a measure of the spread of set of points around a center of mass. Look at it, set of points, measure of spread of set of points around their center of mass. So, covariance is a measure of how much each of the dimensions vary from the mean with respect to each other. So, that means you have set of points here, that is another point. How much of these set of points actually vary from the mean with respect to each other. So, this is what is the difference between these 2 points, and these are the distances of these points. This is for point 1, let us say, this is point 2, this is a variance, right. So, with compare to distance between these points, how the distance from the mean actually vary, that is what is covariance. It is a measure between 2 dimensions to see if there is a relationship between 2 dimensions. So, covariance actually provides you relationship between these 2 points 1 and 2, because we are calculating how the distance between these 2 points varying with respect to distance from these points and the mean, that provides us the correlations. So, I hope you understand. Variance is easy to understand. You have a mean, from mean how much is the distance between the mean and the point which you are talking about it, interested. Covariance is the two points, a set of points around the center of mass, and then you measure how each of these dimensions, each of the dimension means the distance between these 2 points are varying from the mean with respect to each other. So, let us do that. So, covariance is very easy to define. Mathematically it is like this: covariance x y, x and y is what? Summation 1 to n x bar, this is x1, there is something wrong, this is what it is, right. So, let me write it down there, that is very important. Covariance, right, it is defined as like this. So, what you are writing? Covariance of x y, right, yes. So, we have to sum it over I 1 to n x I x bar y I y bar n minus 1, okay. That is what is defined as a covariance, right. So, what are each of these? Obviously, x and y, x I and y I, they are what? They are the data points, and x bar and y bar, they are actually mean. So, we are taking 2 points, one x y and a y I, and we are calculating difference distance of the mean. So, we can always put in as terms of a matrix. Can you see that this is covariance of x and y? So, in a 3-dimensional data, we can make CO convolution x y, convolution x y, sorry x x something. This is x x, x y, x z, convolution y x, y y, y z, convolution z x, convolution z y, convolution, and this is this one. What is the elements along the diagonal? That is called variance. This is what is called variance. There everything is same, right? X x, y y, z z, right. So, diagonal is the variance of x y z, and if covariance of x y is equal to covariance of y x, then matrix is always called symmetrical about the diagonal. Those of you who know a little bit of matrix algebra, they can understand very easily, right. So, that is what is called covariance. Remember, we are talking PCA and we are bringing the new concept of covariance, because that is how the 2 variables, how they are correlated or not can be understood. And let me go back and tell you, covariance is a measure of how much each of the dimensions vary from the mean with respect to each other. So, with respect to x and these 2 points 1 and 2, how much is the dimensions, that is distances from the mean is varying. That is what is telling about the covariance. That means, how these 2 are correlated with respect to mean can be easily obtained from that. Now, you can also have positive covariance, negative covariance. You can clearly positive covariance varies like this, from negative to positive, negative covariance varies from positive to negative, right. That is what it is. So, what is PC actually? As we tell you, this is a linear transformation that chooses a new coordinate system of data sets such that the greatest variance, remember the greatest variance by any projection of data sets comes to lie on the first axis, and second greatest variance lies on the second axis. So, you know variance now, you can calculate the greatest variance. So, greatest variance of any projection of data comes to lie on the first axis, second is lying on the second axis. So, PCS can be used to reducing dimension. So, let me tell you again, this is a linear transformation tool which chooses a new coordinate system for data sets such that the greatest variance, remember this, greatest variance of any projection can be done using many ways. Data sets come to lie on the first axis, and the second greatest variance comes in the second axis, that is called first principal component and second principal component. Okay. And how do you do that? Okay, you can do easily by using what is known as a linear algebra. That is what is called linear algebra, in the sense it is basically eigenvalue eigenvector problem. These are linear algebra concepts that we need to compute from the covariance matrix in order to determine the principal component. So, what we do is we find out the eigenvalues and eigenvectors of the covariance matrix. I have given you covariant matrix here 3 by 3. So, you can actually use the covariant matrix, find out these values. So, how do you find out that? So, you know whenever you do a what is called eigenvalue eigenvector problem, you know what you do, right. Let us say you have a n by n matrix, A is a n cross n matrix, A is a n cross n matrix, right, and V is a vector, right, and lambda is a scalar. So, now A lambda is equal to V lambda, that is what correct, right, A lambda, AV, sorry, not AV, AV is equal to V lambda. Once you solve that equation, you find out the values of this. So, this is nothing but A minus lambda V equal to 0. Once you solve this equation, you find out the eigen values. And once you find out the eigen values, obviously you have 3 by n by n. So, you will find many eigen values, then lambda I to lambda n will be your eigen values. And for each lambda, whatever vectors you will get is called eigenvector. Many people call it eigen. Okay, that is the standard approach which you use in normally in the mathematics, right. That is the standard approach you use in mathematics. So, we write sometimes is basically A minus, sorry, this is I, identity vector, A minus lambda divided into identity vector is equal to 0. Okay. So, that is how you solve the whole problem. So, you have to find out the covariance matrix, then find out the eigenvalue eigenvectors of the covariance matrix, and once you do that, the eigenvectors, the largest eigenvalues, eigenvector corresponding to the largest eigenvalue will be the strongest correlation in the data sets. So, that will be the first principal component, and second largest value will be the second principal component of your matrix. So, you can from your data you can find out the covariance easily, right. You can easily find out the covariance from your data, and then from covariance you can find out the eigenvalue and eigenvectors. That is how we can find out the principal components. The eigenvalue and the eigenvectors are the key, the important always in pairs, they come in pairs, right. They are like that, they are such that they always come in pairs. That means every eigenvector has an eigenvalue. So, also the number of their number is equal to the number of dimensions of the data. So, a 3-dimensional data says there are 3 variables, therefore, there are 3 eigenvectors with 3 corresponding eigenvalues. So, that is how actually we can actually treat this whole problem PCA or principal component analysis. This techniques can be used for dimensional reduction that identifies the set of orthogonal excesses called principal components, and that capture the maximum variance in the data that we talked about it. The principal components are nothing but linear combination of the orthogonal variables in the data sets and are ordered in decreasing order of importance. Highest variance then second highest, third highest, fourth highest, like that. So, we always take the first two important high variance. Total variance captured by the principal component is equal to total number of variants in the original data sets, that is also true. So, that is about the PCA, and PCA has another important particle feature vectors, and in the last slide we have computed the eigenvectors, eigenvalue side, we have shown you how to do that. And now we can further choose whether to keep all the components or the data, discard some of these lesser significant low eigenvalue vectors also, and that is actually called a feature vector. So, we may not take all the eigenvalues, we can remove the lower eigenvalues vectors also. A feature vector is simply a matrix that has as many columns as eigenvectors of the components that we decide to keep, and that decision is made by the user. You may ignore some of these low eigenvalue vectors. And last thing what you do, it recast the data along the principal component axis. This is the last step. So, whatever data you have, you can actually replot it, and that can be done. I think I'll tell my TAs to do such analysis and show you in this week itself, so that they can explain you how the principal component analysis is done. So, with this I come to the first part of the lecture, and next part we will sum it up.